So finally we are now able to write a formula for Euler's phi function. Say you have an input n which is the positive integer greater than 1. Phi of 1 is 1 that we already know. So let n be greater than 1. Then it has a prime factorization like this by the fundamental theorem of arithmetic. Then phi of n is this product, where you can clearly see that this factor is nothing but phi of p1 to the power k1. This one is phi of p2 to the power k2 and so on. From these factors, if you take these powers out, then inside you are left with these things. But when you combine those powers outside, you get n. So that's why in place of this product, you can also write this. Now let's prove it. We start the proof with two things. The first is that phi is multiplicative, that we proved in the previous video. And the other is this observation that if you consider distinct prime powers, where the primes are distinct for different I and j, you consider pi to the power ki and pj to the power kj, then they are relatively prime. So because of that, phi of n, which is this, can be written like this. This comes from this relative primality and the multiplicative nature of phi. If you are wondering how we can distribute phi over this product like this, you do it in steps. First you note that p1 to the power k1 is relatively prime to this product. So there you distribute phi once, you write this phi value as phi of p1 to the power k1 times phi of the rest. Then you continue this process. So that's how you get it. You can do it by induction also, it's a simple thing. So I just simply wrote like this. And now we know these phi values. We know how to calculate the phi value of a prime power. So by what we did previously, phi of p1 to the power k1, for example, is that power minus the next lower power. Similarly, the other phi values. Then in the next step, you take p1 to the power k1 outside from this factor, and that leaves you with this other factor 1 minus 1 divided by p1. And you do that to these other factors and gather these powers of primes outside, and along with them you have these other factors. This, however, is n. So that's how the proof ends. Let's now apply this formula to next calculate phi of 360 in this example. The prime factorization of 360 is this 2 cube times 3 square times 5. In this form, the formula is the easiest to apply. So we do that. We just write 360 here and then 1 minus 1 divided by the prime and such factors. So you get these things, and then when you do the calculation, you get 96. When one studies phi values of integers, one encounters this fact, and with this result this section ends. Theorem 7.4. If n is greater than 2, then phi of n is an even integer. The proof is divided into two cases. In the first case, we consider that n is some power of 2. Because n needs to be greater than 2, so this exponent k cannot be 1. Because if k is 1, then n is 2. So k needs to be itself greater than 1. In this case, phi of n, if you apply your formula, it ultimately becomes 2 to the power k minus 1. Because k is at least 2, so this is divisible by 2. So that means phi of n is even in this case. But if that's not the case, that's not how n is, then n has to be divisible by at least one odd prime. Say p is such a prime. N may be divisible by many odd primes, but at least one odd prime is there which divides n. So then n will be of this form p to the power k times n, because p needs to divide n, k is a positive integer, and at the same time we have conveniently separated the power of p completely from the rest of n, which is m. That means the GCD of p to the power k and m is equal to 1, which just simply means that p does not divide n. So we then calculate phi of n. which is phi of this. Because p to the power k and m are relatively prime, so that becomes phi of p to the power k times phi of m, because phi is multiplicative. And this becomes this difference, from which if you take p to the power k minus 1 outside, you are left with p minus 1. Note that we are not taking p to the power k outside, but rather p to the power k minus 1. And you just keep phi of m as it is, don't have anything to do with that. Now note that since p is an odd prime, so that's why 2 divides p minus 1. P minus 1 is even. So in this case also phi of n is even. So here the proof ends and this section itself ends. So next week we are going to start exercises.